Hello, everyone, and welcome to the 2020 DOE Online DOE Summit presented by Statasys. And today we'll get you another daily dose of DOE. Today we have the presentation Use of DOE for 3D Printer Ink Formulation Development by Dr. Gregory Zadok. And let's see. Now, Dr. Zadok is a senior research chemist at Stratasys with many years of formulation experience under his belt, as you can see here. And I'll hand the presentation over in a second, but first, as questions come up, we'll have a question and answer period near the end of the presentation. As your questions come up, please feel free to type them into the questions area on the menu on the right-hand side of your screen. When we get to the Q&A section, we'll read them out and get them answered for you. So, without further ado, I will pass the presentation on to Dr. Zadok.
Yeah, just right.
Okay.
Okay, so hopefully now you're seeing the presentation view.
Oh, yes, we are. Yep.
Yeah, great. Oops, where did it go? Right. Okay, so thank you, Greg, and thanks to Statasys for allowing me to present my work. I'll be talking about DOE of mixtures in ink formulation development. This is an area that is fairly recent for Stratasys. It was not being used at all before I came along and convinced everyone that this is the way to go. And that's partly because I'm lazy and I don't like to do a lot of experiments. So I'd rather do the minimal amount of experiments needed and have the maximum amount of results. So just to be on the same page and so you know what to expect, I'll begin with introducing the company I work for and the specific technology that we'll be discussing today. I'll give a little bit of information about typical ink formulations for UV curing, and specifically about support materials, which is I'll discuss what they are and what they are for, which is what I've been researching for the last 3 years almost. And then we'll go on to the use of DOE for these formulation developments. And then at the end, I'll give a little bit about my thoughts and experiences using DOE for formulation development. Right. So Stratasys, as you can see, we have many installed printers around the world, and we have been around for about 30 years. Stratasys today is actually a merger of two companies, an American company based in Minneapolis, which was called Stratasys, and an Israeli company based in Israel, which was named Objet. And these two companies merged in 2014. And the merger was successful because, I forgot about this slide. This we are installed, or we operate in many areas around the world. The two companies merged because they had different technologies. Stratasys USA had a FDM technology. FDM stands for Fused Deposition Modeling, which actually means that you take a ready-made filament of polymer and you fuse it or liquefy it and then deposit it on a surface, and then you add layer by layer to get the finished product. Objet, the Israeli company, had a different technology, which was essentially like inkjet printing for 2D on paper, but instead of doing only one layer, you would continually do sequential layers. And polymer, so that means that you deposit, well, I'll talk about it later, but essentially the polymer is being prepared on the tray. So that means that we deposit liquid material on the tray. When the UV lamp passes, it polymerizes this resin, and this is done sequentially for each layer. On the right, this is what our printer looks like from the inside. Usually you don't open it during operation, but we did it for this, for photographing the machine at work. So essentially the jetting head moves along the x-axis and if the printed part is larger than the print head, then it also moves along the y-axis to allow for another layer of the same height. And as the model grows, the whole tray, the build platform, is lowered along the z-axis to allow for a constant distance between the jetting heads and the printed model. So our polymers are acrylic polymers. I'm on organic chemistry, so I had to put in a little bit of organic chemistry. We have several types of monomers and sometimes, not always, some difunctional oligomers. We UV cure them, so we get a chain. I will talk a little bit about this process in a minute. And then at the end of the process, we get a network or a cross-linked polymer. So the resin that we have is actually a mixture of monomers, oligomers, sometimes non-reactive materials, which are not shown here, and photoinitiators. The photoinitiators are the ones that begin the reaction. So hopefully you will see a light of flash now. And then after the light of the UV lamp goes over the resin, the photoinitiators turn into reactive species, and these react with the monomers, and consequently the reaction continues until all the material is used up, and then we have a cross-linked polymer. So a typical UV curable ink formulation has several components. A monomer, which is the main chain former. You need a main chain in order to get a polymer. We have also oligomers, which usually are multifunctional, difunctional or trifunctional. So they cross-link the chains. They determine the distance between the chains, and subsequently they determine some of the properties of the material. If they are long and flexible, then you might get a flexible material. If they are short and rigid, you get a rigid material. This is a bit an oversimplification, but this is more or less what happens. In addition, you have non-reactive materials, some of which affect the properties of the polymers, like the TG of the polymer. So you can have a rigid polymer and you can make it softer just by using some non-reactive materials. They also affect the surface quality of the model, sometimes, not all of them. There are also some that determine the color. So if you want to print a colored piece of plastic, you would need pigments and stabilizers, dispersants, and other materials to get everything in solution and to have it stable over time. So we also have photoinitiators, which, as I said, they initiate the polymerization reaction, but they also have an effect on the finish of the top surface. So some photoinitiators leave the surface sticky or not very nice to the touch. So you sometimes need to use other photoinitiators to get a more smooth finish, which will be less sticky. In addition, we have to have some kind of inhibiting agent that, because during storage, sometimes the radicals are formed spontaneously, and you wouldn't want the reaction to start during storage. So they are actually sort of radical scavengers. They scavenge the small amount of radicals formed during storage, and they enable a longer shelf life. And also, last but not least, you have surface active agents, which have regulate the surface tension. So because that is required for the print head calibration. So you need a certain surface tension in order to be able to jet the ink. But they also affect the surface quality of the model, how the model looks at the end. And we will see in a minute why that is important. So this is a layer or a model that was printed. It's very thin, so we can see through it. It was built from the bottom part to the top, and this is a support material near a model material. This is the same formulation, but with different levels of surfactants. And as you can see, for one layer, you might not notice the difference, but when you build a few hundred layers, then you might see a difference in height at the interface between the two materials. And also, if you, let me just get the pointer. If you can see these type of hairs here and here and on the other side, it depends also on the direction at which the printhead goes. So the printhead goes along the x-axis, as I said. So at the beginning, it goes from left to right, and on the way back, from right to left. So you might have a different surface quality at the two ends of the model material. And just by changing the concentration of the surfactant, you can affect these layers, sometimes in a good way for the hairs, but in a bad way for the difference in height. So you need some type of balance to get everything in order, and that's the work we do. So it's a matter of selecting the right surfactant and also the right concentration. So let me talk a little bit about support materials. Why do we need a support material when we are printing in 3D? Because sometimes you have overhangs, and since we are not depositing a viscous polymer, but rather a resin, which usually has a very low viscosity, you cannot deposit a liquid over air. So you need to deposit it on something solid. But this something solid has to be something different than your model material, because you need to remove it at a certain point. Also, when you have a mixture of support material and model material, you get a different surface finish at the areas where the support material touches the model material, and a different surface and another surface finish where there is no contact between the two. So in order to have a more comprehensive look for the overall model, so the finish will be more or less the same in all directions, you would coat it with a support material all over, and then you would get a better a unified look for the model material. So the support material has to satisfy several conditions. It has to be compatible with all the hardware. That means the print heads, the tray, all the tubing, the pumps. So we have to be very careful with the materials that we choose. It has to be compatible with model materials. So right now we have maybe tens of model materials, and we have to check the new support material to be compatible with every one of them, which is a challenge. It doesn't always happen. So if we know the limitations, we can limit the use of the support material for certain model materials. It also has to be rigid enough to support its own weight and that of the model material, meaning if you print a cube of support material, you cannot have it deform under its own weight. So it has to be rigid. And then if you deposit a model material on top of that, it has to be rigid enough to withstand the weight of the model material. And also, we have to bear in mind that the printing area gets quite hot. And I will talk a little bit about that later. It gets quite hot, so it has to be rigid at the working temperatures. So this is also quite a challenge, and that's actually the challenge, the biggest challenge that we had to overcome. And also because it is a support material, you have to be able to remove it easily from the model material. I mean, you wouldn't want it to stick so hard that you cannot remove it. There are several ways to do that. In this picture, which is not ours, I have to say, this is a soluble material. So you would place everything in a cup of water, and then after some time, all the polymer, all the support material would be dissolved, and you would and what would remain would be the finished model without any support. So that's one way. Another way is to remove it mechanically. So you would, what we have commercially available is what we call a water jet, which, as its name implies, it jets a thin stream at very high pressure onto the surface and just mechanically removes the support material from the model. And after we've done all of this, you would need to have good surface quality of the model, because if the model looks bad, nobody will print anything. And of course, it has to satisfy the viscosity for jetting, which for inkjet materials is very, very low. So we are very limited with the types of materials that we can use for formulation. And this is a real challenge because, of course, you could increase the temperature of the print heads to match the required viscosity, but you can go only so much high. You cannot get higher than, I don't know, maybe 80 degrees centigrade. So working with all these challenges, we had to develop the support material. So we had the starting formulation. That was my goal when I came to work for Stratasys about 2.5 years ago. They gave me a starting formulation, but the surface quality of the model was very, very, very bad. And it also contained a non-reactive material, which we didn't want to use. We would rather not have used it because it tended to leak out of the polymerized material. And so I tried changing the formulation using the classical approach, just change one thing at a time and see what happens. And this is what we got. It would melt during printing. So if the model was, I don't know, maybe 2 or 3 centimeters high, everything would look fine. There would be no problem. But as you got higher, these models, I believe, are about 7 centimeters high. When you would get about 5 centimeters, everything would start to melt. And of course, this is not what we want. We want everything to be nice and have a nice shape, nice straight edges. But this did not happen. So we concluded that we needed a more rigid material that would be able to withstand all the heat generated during the polymerization reaction and, of course, from the UV lamps themselves. But the formulation had 12 non-reactive, 12 materials, including the monomer, and it was too many to understand the effect of each one of them. And when I asked, okay, how did you get to the formulation? What is the purpose of each of the ingredients? No one could tell me what everything does. So I decided that using DOE would be the only way possible to understand the effect of each of the ingredients. And that's what we ended up doing. So just now for a side note, since then, we have done many DOE experiments, and we have come to the conclusion that it usually halves, at least halves the number of experiments that we need to do to get a good result or a very good candidate, which can then be turned into a product. So why don't people always use it? Well, first of all, the researchers themselves, some of them don't like to use it. They say, I didn't go study chemistry or engineering to be a statistician, and I don't understand this, and I don't want to use it. So this is a challenge that we have to overcome. Well, and it can only happen through successes and education. The other thing that I encountered during my work was the managers. They don't like to wait 6 weeks or 5 weeks for a result. And sometimes you have so many experiments that need to be done and you don't get interim results. You have to wait till the end to see the final outcome. And this can be a challenge for a research scientist like me. Say to the manager, okay, come back in 6 weeks and I'll give you the result. And of course, there's the question of expectations. What if it doesn't work? What if I did everything wrong and I don't get a result? So we lost 4 to 6 weeks of work, and what now? And since we are all used to be pressured for bringing results on time, this can be also a challenge. But fortunately, my manager understood all of this and allowed me to experiment with DOE, although we didn't have any experience with it before. So we had 12 materials to screen, and we decided that for the screening phase, a linear model would suffice. We just wanted to see if things had an effect. So, I mean, I won't go into details, but we had one monomer, which we varied, and also 6 non-reactive materials. We also had 3 PhotoInitiators where most of the constraints were posed. Although the limits for the PhotoInitiators were between 0 and 3%, you need to have some PhotoInitiator for everything to work. As the instructor at the Statasys course for mixture said, in order to design for a cake, you need to be able to make a cake. So we needed some PhotoInitiator, so that was one constraint. And also from previous experimentation, we knew that for PhotoInitiator 2, which is labeled here J, we needed at least 1%. So the second constraint, this one, was to ensure that when no other PhotoInitiator is present, then J would be at least 1%. And we also had 2 surface active agents, which we didn't know which one would be best, and if we maybe needed a mixture of both of them. Everything does not add up to 100 because we had an inhibitor, as I said, and it was kept constant. And then we also, initially, we added a constraint for viscosity because you cannot have the viscosity too low, otherwise the printheads won't be able to jet, and it can't be too high for the same reason. So we had to keep it between a reasonable range. We calculated the viscosity based on simple linear addition of the viscosities of each of the components at the required temperature. But we knew that that experimentally, that we knew that this was not exactly correlated. So we gave a little bit more margin for the software to be able to work with. All right, so we had the budget for 25 runs, and had I heard the previous lectures that were given last week, I would have kept some runs in reserve and perhaps done some only 20. And maybe I would have excluded the factors that I knew would have an effect, like the monomer. It was obvious that you would need some monomer and that it would have an effect on the overall quality of the material. And then maybe we could have done less experiments. But That's the fun of it. I always learn something new. For the screening, we used the optimality, and we had 19 responses. Some were measurable, like the mechanical properties of the model materials, or viscosity was one of them, but most were subjective. That's one of the problems that we have, that the quality of the printing can only be assessed by an expert panel, which is good for screening, because during screening you get either very bad models or very good models, so there is enough variability for the expert panel to be able to judge. But from my experience, when you do an optimization DOE experiment, the differences in quality are so small and are smaller than the differences in opinions of the expert panel. And so usually we don't get very good results from optimization experiments. The problem, as I said before, this takes a long time. Printing in 3D takes a very long time. So we could only do 2 or 3 formulations per printer per week. We only had 2 printers available. So it would have taken 5 to 6 weeks in total. And as I said before, having my managers wait for 6 weeks before I could tell them anything was challenging. So we started the experiment, and I'll talk about the highlighted experiments in a second. Everything was going fine until we got to run number 5. We prepared most of the formulations beforehand, before starting, so the printers wouldn't wait for formulations, just to keep the downtime of the printers to a minimum. So when we got to run number 5, it turned out that PhotoInitiator 3 was partially insoluble in the formulation. So if I learned one thing, is make sure that you can make the cake each and every time. So we had to stop everything and augment the design with new limits for PhotoInitiator 3, and we had to compensate that with PhotoInitiator 2, which are similar in structure. So we thought that they could be interchangeable. And so we augmented with the new limits, and some experiments went fine. As you can see, we have experiments with 1.5% of PhotoInitiator 3, but not all of them. That, of course, depends on the exact composition of the formulation. So we discarded all the runs with PI3 over 0.5%, augmented the design again with more experiments that we needed, and discarded all the ones that had PI3 in them at all. And we ended up having an experiment of 27 runs, which was a little bit over budget, but it was needed to have an adequate design space, because otherwise, if I would have discarded too many experiments, the design space would have been too small. And so finally, after almost 2 months of experimenting, we came to the analysis part, and I find that the most useful graph is the Pipel trace graph. For me, it's the most understandable. I can relate to it. I can understand what's going on. Because our requirement for viscosity is very, very strict. We fitted also the viscosity, or the experimental viscosity, to the linear model, and it was actually very, very good. The fit was very good. So why did we need that? Because if I had found that everything had an effect, either for good or for bad, or for better or for worse, it would have been difficult to adjust the viscosity and maintain the required qualities. So I had hoped that some of the materials that we screened for were not going to have a very large effect, or any effect at all. And so these could be used to adjust the viscosity after or when the optimal formulation was found. And so we used this information later to design the other formulations. And also, fortunately, all other parameters like the print quality and all other measurable qualities, as I said, like the tensile strength and other mechanical properties, most of the graphs looked more or less the same. So that means that most of the ingredients had a very similar effect. As you can see, these materials didn't have a large effect, so we could use them to adjust the viscosity later. And we got very useful information regarding the materials that actually had an effect. And there were no contradicting effect. That means for almost all of the required qualities, the same materials were used to better the formulation. And so we didn't have any contradicting effects, which was fortunate. It doesn't always happen. So we performed a numerical optimization on all of the parameters and to find the so-called sweet spot. But it was not optimization, so it wasn't really a sweet spot, but we wanted to know which formulation gave the best surface quality and other attributes that we needed. And fortunately, it was very similar to one of the runs. But surprisingly, we expected that the best formulation would be rigid because that's what we set out to get. But instead, it was more like a rubbery material, which was hard, quite hard when it was cold, but it was more flexible when it was hot. We couldn't explain why it worked, but it worked. Because when it's hot, it should have been like sort of melting, but it didn't. And this was very, very fortunate. And actually, we continued with this direction for the rest of the optimization of the formulation. And this formulation was in an experimental region that we hadn't gone into before. We didn't explore it, and actually, had we have come across this formulation without the use of DOE, we would have discarded it as something that was not feasible. So to summarize, sometimes it's daunting when you have too many experiments. I know it's very difficult for people to understand that having a list of 20 or 25 experiments to do is very difficult. Just beforehand, knowing that you have to do so many experiments, most people prefer to do an experiment or two and then continue on from that, having some results. It's difficult to do 25 experiments without knowing what's going on. And also, it's, from my experience, it's very frustrating that most of the experiments turn bad. And I like to explain to the people I work with that bad results are good, because that means if everything is good, then you don't know anything, you don't gain anything. Some results have to be bad because otherwise you wouldn't be able to understand what is going on. And we learned from our mistakes. We now validate the ingredient limits before we start the experiment or before we start the design, to make sure that the cake can be made at all and not to run into the same problems we had before. But we also have to be careful when restricting the design space, because then we can lose some of the information, and we can, if we restrict the design space too much, then we might not get surprising results, something that we didn't think of. So yes, we have to have as a large design space as possible within the limits that are possible, because sometimes the results are surprising, and surprising results are good. So thank you very much for listening in, and back to you, Greg.
Awesome. Thank you, Ori. Let me bring the presentation back over. Okay, so let's move on here. A couple of housekeeping things while you all can type up your questions in the question area on the menu to the right-hand side. First thing, the slides for this presentation have been posted on the Statasys website, statasys.com, in the webinar area. We will have a recording set up later today after the file gets processed. We'll get that posted. In the meantime, as some of you know, we've been doing a special offer for distance learning workshops. We've actually decided that we've just removed the need for the special code or anything. So we've just reduced the rate on all of our workshops. So head on over to Statasys and look into the training and the distance learning area for a list of the upcoming workshops. Okay, so let's see, let's move on to some questions now. Let's see, we've got time for a few questions, and let me get over into that area in a second here. Okay, all right. Okay, this one, the first question comes from Ashay MS. What performance parameters was used for analyzing the product performance as a response post 3D printing? In other words, dissolution or disintegration, etc.
So disintegration of what? I mean, we have a model material which doesn't disintegrate. We look at the model itself. I mean, post removal of the support material. So some of the parameters were, let's say, ease of removal. That depends on the exact support material that we use. So if, let's say, if you want mechanical removal and the support is so rigid that it cannot be removed by a water jet, then that would be a bad performance. But mostly we look at the parameters of the model material, what remains after the removal of the support material. And that's usually a visual inspection of an expert panel. We have print quality physicists who have experience with these models, and we always compare it to the current materials that we have, or the current like state of the art of the commercial materials that we have. And of course, the goal is usually to have a support material which gives a surface quality which is at least as good as what we have now, hopefully better. And of course, the added, we have to have some added value, which would be ease of removal or ease of processing, depending on what we develop at the moment. So usually we look at the model materials, the mechanical properties of the model material. Because of all the hairs that I showed in one of the pictures, when you print in matte, which means that the whole model is covered by support material from all sides, then you get reduced mechanical properties. But we can't have them reduced too much, because otherwise everything would break by touching it. There are also some other parameters that I won't get into, like the printability of thin walls. If you have a very thin wall and you have support on either side, and you have, well, we call it a mixing layer, because by nature of the droplets, they are liquid droplets. When a model droplet is deposed near a support droplet, they might mix, depending on the exact formulation. If they mix too much, then you get a layer which could be very large. which is a mixture of model and support. When you remove the support, you remain with this mixed layer, and this has an effect on the appearance of the model and also on the mechanical properties of the model. So that's what the surfactants are for, to make sure that the interaction of the droplets is such that it doesn't give a very large mixing layer. So
Okay.
more or less, so as I said, we look specifically most of the time at the qualities of the remaining model material after removal of the support material.
Okay. Next question comes from John Davies Jr. And he asks, did all 25 formulations produce a usable viscosity as expected? If not, did you adjust viscosity or change the design? With so many components, seems like viscosity could be very different for each formulation.
Well, yes, the viscosity was adequate in all of the formulations. I didn't show the results of the experiments, but yes, it was, as I said, the actual viscosity was a bit off. It wasn't exactly as we expected, but everything was within an adequate range. The range that we selected was a bit smaller than the actual range that we can feed to the print heads. Usually it's between, well, depending who you ask, but it's between 10 centipoise and maybe 25 is the maximum. So the limit that we set, 12 to 22, gave us a little bit of leeway on each side if we were a little bit further from the expected range. We usually try to be between, let's say, 13 and 18 centipoise, with the target being 15.
Okay. Next question is from Robin Wright, and the question is, in the Pipel plots, how do you select the reference blend?
Well, the software usually selects it as the center point, if you have it. I think it doesn't really matter because the center blend is arbitrary. So, well, in Design Expert, you can actually select any of the experiments to be the center point. From my experience, it doesn't really matter which experiment you choose as a center point, because what the plot shows you is what happens when you move away from this point by increasing or reducing the concentration of a certain ingredient. And so the plot itself, it looks different, but the results are the same. So.
Okay. All right. The next question is from Arvid Harding. Hi, Arvid. Should you have used the printer as a block variable since you use two printers? Did you notice any differences between the printers with the replicates?
Yeah, I knew this question would come up. We thought about it, but we decided that we know that there is a variability between the printers, but we decided that for one thing, we didn't want to waste an experiment for blocking, and we know that the variability between the printer can be quite large. So we were aware of that, and but we didn't use the blocking in the experiment. We did it other times in other experiments. We didn't see a huge difference in print quality, which is good. That means that our customers can expect to have a similar quality no matter what printer they have. But there was one time I wanted to show it, but I decided that it would be too long. That we had one of the advantages of using 3D printing is that when you have moving parts like a gear or interconnecting gears of some sort, you can print everything at once. You don't have to attach the gears to a scaffold or anything. So you can print the scaffold with the gears, and between the gears you would have support material. And then when you remove the support material, the gears should be freely moving. And so in one of our experiments, we printed the moving gear part. And then we noticed that some gears turned and some didn't. And so luckily we had a blocking parameter. And we discovered that it was printer dependent. I mean, you would have expected that it was formulation dependent, but it was not. All prints from one printer gave movable gears, and all prints from the other printer didn't. The gears didn't move. So we asked ourselves why and started to investigate. And then we found it was a difference in software version. I mean, the printer software was a different version, and they changed something in the print setup, and that was what gave the difference. So usually when we perform DOE experiments, we make sure that all the printers that we're using for that specific experiment have the exact same software version. So I hope that answers your question.
Okay, yep, and that seemed to come up in some other questions as well, same talking about blocking. Okay, next question, another one from John Davies, who asks, what was the reaction from leadership after the DOE was a success? Did they want to continue with more DOEs?
Yes, actually, yes. Yeah, they were very excited, and they decided that most of the R&D personnel would undergo a DOE course, and that they would use DOE not only for mixtures, but also for in our alpha testing of the printers. Because right now what they would do is they would perform all of the experiments on all of the printers, and that would take a huge amount of time. And of course, with DOE, you can mix everything up and use far less experiments on the available printers, and that's what they've been using since. So yes, in that sense, yeah, I take credit for that.
Awesome. All right. Next is from Niels Decker, who asks, the design was not an optimization design, but you still used it to find a best example, which is more optimization. Do you see this work more often, as it means not many interactions have a lot of impact?
Well, it really depends on the formulation, but as I said before, at least from my experience in this field, in the 3D printing, when we tried to perform optimization experiments, the differences in print quality were so small and were smaller than the differences in opinions of the various experts that we use to judge the print quality. Because I mean, I wish we would have some measurable factor that we could use for assessing the print quality, but as much as we have tried, we don't find any. So we need to use the opinion of our experts. And as I said, the differences in quality are smaller than the differences in opinion, and we end up having insignificant results. And we tried that once, and maybe we'll try it again, but I'm not sure. So we usually do screening experiments. The optimization, once you know the exact what factors have a major effect, then optimization is usually just a matter of trial and error.
Okay. Next question is from Gregory Perrine. And let's see, he says, do you anticipate you will use mixture / process designs in the future to understand the interaction of printer settings/factors with your mixture?
Yeah, that's a good one. I would like to do that, but I think that because the experiments take so much time, well, there are two main problems in our industry. One of them is that replacing a material with another material takes about 4 to 6 hours just to replace the material, and then we have to calibrate the drop weight for each material, so that it may take half a day just to replace a material and have the printer ready for the new prints. That's one thing. So it limits the amount of times that we can replace the materials. It also takes a toll on the material. I mean, our customers usually have a set or a fixed set of materials that they use and they don't change them. So they just change the cartridge. We assume that everything is going to stay the same, and well, we have no problems. In the R&D, we switch materials almost daily, and it takes a toll on the printers. That's one issue. But mainly it's the issue of time. Losing half a day for changing a material is bad enough when you have just a mixture experiment. If you add process variables to that, you get a huge amount of experiments. So if I would have to optimize just one or two ingredients with printer parameters, yes, maybe we would do it, but we haven't had a chance to check that out yet. I know that Design Expert 12 and onwards have I think it's a KCV model. Am I correct? Did I say the right letters?
Yes.
Yeah. To reduce the number of experiments, I would love to try that. Waiting for the right set of variables to use on that. But yeah, I hope we do find the right moment to use this mixture and process variable.
Let's see, there are a couple of people who were commenting, not really questions, but just commented on how much they liked your comments about learning from your mistakes and bad results are good. They sort of pass that along.
Thanks.
And then Diane Williamson, she says, this is a comment rather than a question. When working with a formula, sometimes you have an idea of what won't work. So what we do is look through the experiments and run some of the extremes. If we run into a problem, then we can just adjust the limits.
Yes, we did that, and it seemed that it would work, but we didn't take into account that in some, because there were so many components, in some instances, the material didn't solubilize, and it was difficult to understand when it did happen and when it didn't. So we ended up not using it at all. And actually, in the subsequent formulations, we discarded it altogether and we decided not to work with it.
A couple of things. One was another comment from Arvid Harding, who says, to help with process mixture experiments, consider split plot experiments with formulation variables as hard to change. Says just some
well,
info.
As I said, we haven't come across a specific project to do this on. I'm still looking.
Let's see, and I think we have time for one last question. Another question from John Davies. Did each of the 25 formulations require custom blending procedures, order in which components are blended in, or were the components simple to mix?
Well, in our specific formulations, sorry, usually there is no special procedure for making the formulations. You just throw everything into a pot. If we have solid components, then we heat everything up, mix it thoroughly, and then just mix it and then sieve it. So no, there is no special, at least in these formulations. But if I may comment on your comment, when we do DOE experiments, we try to have a sort of I don't know how you call it in English, like a fixed blend, and add to that some of the other ingredients. In this case, we prepared everything from scratch. I mean, because we varied everything in the formulation except one component, there was no reason to do a fixed blend. But in other cases, when we just look at some of the components and not all of them, we fixed most of the components and then just changed the ones that we want varied. So we prepare a batch or a fixed batch and then add to that.
Okay. Well, I want to thank you, Ori, for doing this presentation. I found it really interesting. One, for an insight into 3D printing and all of the issues. I found that fascinating, and also your use of DOE during the whole thing. Tremendous. Thank you so much for being here and giving this talk.
Thank you for listening to me.
Yeah. All right, everyone. Well, hopefully we will see you again later in the week at some of our other webinars. And but for now, we'll say thank you and good day or good night. Take care now. Bye-bye.
Thank you.